soft collinear supersymmetry. This is in collaboration with Tim Cohen, who's also at Eugene, and Andrew Larkarsky, who was in Harvard but is now in Reed College. And we have 2 papers on this already, so you can see this for more details. Okay. So there's this effective theory called SCET. And if you spend a lot of time at MIT like I did, you hear about people using this for all kinds of things, like LHC calculations, having meson decays, even recently limp dark matter systems. And so kind of almost the simple question to ask is, can you consider the SCET limits of more general theories? For instance, the supersymmetry have a SCET limit. Can you extend that to supergravity? What about pure gravity? And because it's such a powerful formalism, can we maybe hope to learn interesting things by doing this, both from a formal and perhaps a phenomenological perspective? So that's the question we asked. Let me actually motivate SCET first. So gauge theory has, as we all know, soft and collinear divergences. So for instance, if you just look at, in this case, the U1 gauge boson emitting off of a fermion, you can write down the amplitude for this process, and you can see that this amplitude diverges in the IR, in the infrared. So that is to say, if you take the momentum of the photon to be soft, to be very small, this thing diverges. If you take the photon momentum to be collinear to the fermion momentum, so they're very collimated, this thing also diverges. And this is the reason why we see things like jets, and this can explain a lot of the phenomenology that we see. So the existence of IR singularities motivated the development of SCET. And you can, originally it was motivated to resum these IR divergences. So processes where what you're looking at, the cross-section, is dominated by modes that are soft or very collinear. And then you can actually do better than you can in ordinary perturbation theory. You can think of SCET as, it's an effective theory, but instead of an expansion in mass scales, it separates physics with different momentum. So it separates, the physics factorizes so you can have a particle that's very collinear, and that physics can be described to leading order independently of a particle that's very soft. And this requires the existence of a small power counting parameter. So instead of having like a mass scale, you have some other parameter, and that depends on the details of your process. And then what you do is you expand your fields along this light cone direction. You integrate out modes that are away from the light cone, and you construct your theory like that. And the first thing that you might wonder, because we're trying to write down a supersymmetric version of this, is because you're picking a direction, this breaks Lorentz invariance. You have a preferred direction. So originally you see that maybe there's something very non-trivial about trying to supersymmetrize this, a theory that needs the full Poincare invariance. So the outline of my talk today, I'll tell you basically about kind of the first steps to constructing n=1 super Yang-Mills in a consistent effective theory. So in order to do that, first I'll tell you about SCET formulated in terms of 2-component Weil spinors. And ordinary SCET is actually done in terms of Dirac fermions. So even this, we have to spend some time making sure that we did this right. Then I'll just introduce some basics. What does the superalgebra looks like? What do the symmetries look like? And then I'll give you some examples of the simplest kind of models that you could start to construct. So I'll talk about gauge theory, both in terms of components and in terms of superspace. And then I'll talk about the Wess-Zumino model. And why it actually turns out it doesn't work. And I'll tell you a little bit about stuff that we're thinking about at the moment. So, SCET 101, you choose a linear direction. In this case, this is the convenient choice. And then you choose an anti-collinear direction. And you have some freedom in this choice. You basically need these conditions to be obeyed, and then you can choose some vector such that these are obeyed. Once you do that, you can just expand any Lorentz 4 vector, momentum in this case, in terms of this basis of light cone coordinates, right? So you have now these three coordinates. You have a perpendicular direction, you have a direction along your collinear direction, and a momentum along your anti-collinear direction.
Are you imagining that P is in the Z direction in this case?
In this case, yeah. Yeah, exactly. With this choice, it's Z and minus Z. Yeah. Okay, and then what happens is that different modes along different directions or in different regimes of your EFT have different scaling. So, for instance, if you just have what is referred to instead as a hard particle, that particle, every mode will be dominated by this energy scale Q, which is the energy in your event. But then if you have a particle that's along the collinear direction, most of the momentum is going to be collinear. So, and I should say here that lambda is a small number. It's some small scale that comes up in the problem. So in that case, only the collinear direction will have the same scaling as the hard process, and the other two directions will be suppressed. And if you have a photon that's radiated, a soft photon that's radiated with very small momentum, then all the directions will be suppressed. And for this reason, I won't talk a lot about soft interactions in this talk, because to leading order, because they scale homogeneously, things are very trivial. They just have the same scaling. The Lagrangian looks the same as it would for a hard process, just scaled down. Okay, so a physical example of this is, of course, jets. The Airy divergences of QCD lead to these jet objects, colliders. So in this case, you can think of Q being the event energy. So P minus, your collinear modes will be along this direction. There'll be some small transverse component that will go as jet mass in this case, which you can just think of as some number between these two scales. Your anti-collinear modes by conservation of momentum have to have the following scaling. And you can see that this defines a power counting parameter, and that it's going to be small. Okay. And likewise, your anti-collinear modes just have the same scaling, but in the opposite direction. Okay. So now you want to write down your actual Lagrangian for your EFT. How do you do that? And as I said before, I'll work in terms of two-component Weil spinners. So what I call U here is a left-handed Weil spinner. And the first thing that you do for spinners is you want to separate out the collinear from anti-collinear modes. So the modes going along the jet directions from the rest of the stuff. So to do that, you define these projection operators. In this case, where it's just a two-component spinner, these are the same as your chiral projection operators. They have some defining relationship, and if you work these out, you plug in your sigma matrices, what you see is, in order for these relationships to hold, half the helicity states of the fermions are projected out. So that means in the EFT, your collinear fermion has one spin state, or one helicity state. In the choice of basis that we use, it's just the lower component. So if I take my Lagrangian for left-handed fermion, and I just plug in the expansion, I get these terms. The thing to note here is that in this basis, the projection of the derivative with the collinear direction, you can think of this as light cone time. So that means that half of these modes will be propagating and half of these will be non-propagating. So the anti-collinear modes are non-propagating in your EFT, and what that means is we'll want to integrate them out. And you can do that classically, just with the equation of motion, and you find some expression like this. You'll notice there's a strange 1 over n bar dot partial term that comes in. The way to think about these things is in terms of a Fourier transform. So just think of this as 1 over n bar dot p acting on whatever fields. And then it's perfectly well defined, and you can use that to define, for instance, the Feynman rules. So just plugging this back in, you arrive at the fermion Lagrangian. Okay. If you want to add gauge interactions, you just kind of, this is exactly what you might think it will be. These are now your gauge covariant derivatives. The different indices correspond to soft and collinear and different power scalings. But the thing to keep in mind is this is generally the kind of objects that come up. So, as I mentioned before, you pick a light cone direction, you're breaking Lorentz invariance. So what does that mean for your EFT? Well, the sket will still be invariant under a subset of generators that are unbroken. That goes without saying. However, there's an additional requirement coming from the broken generators, and explicitly, these are the broken generators. And the thing is as you start, you're going to have like a leading order expansion, and then you're going to add higher order terms to your Lagrangian in that. And when you add them all back in, you have to get a theory, of course, that's Lorentz invariant. So what that means is, at every order, there is some residual symmetry that Lagrangian has to obey coming from the broken generators. And this is what is called reparameterization invariance. So there's a lot of literature on this. For the purpose of constructing new skets, you can think of this as a consistency condition. So if you construct something from the top down, you have to make sure that all your terms do, in fact, satisfy RPI. Or likewise, if you're just writing down something from the bottom up, you want to make sure that you only write down things that are consistent with RPI. And I'll show you an example when I talk about the Wess-Amina model of why it's important to do these checks. Okay, so practically speaking, what is the manifestation of RPI? Well, RPI basically means that we can shift the anti-collinear direction around as long as these conditions are obeyed. So the actual transformations correspond to these three. You have RPI 1, 2, and 3. They correspond to the following broken Poincare generators. And you can think of them as follows. So RPI 1 corresponds to small deviations of your collinear direction. RPI 2 corresponds to deviations in the anti-collinear direction. And they can be large now because they're going to be power suppressed by this lambda scale. And RPI 3 is just a shift of both axes. So these three symmetries, whatever you write down, whatever Lagrangian you write down, must be invariant under these guys. And so what this means is your fields will transform non-trivial under RPI. In particularly, spinor fields or Lorentz vector fields will have non-trivial RPI scalings. So for instance, the wild fermion that I mentioned, it's decomposed by the projection operators. However, the full theory spinor has to be invariant. So this object here must be invariant, and from that you can figure out how the different components transform. And if you're interested, see our paper for tables of how to do this in two components. Okay, so now let's think about adding supersymmetry. So if I just write down, for instance, to leading order, a theory with a left-handed single...
Yeah. For a second. So just before you get to SUSY, I
Yeah,
guess the advantage of the sket expansion is that you can systematically organize your calculations so that you know what you're neglecting and what you're not neglecting in the soft limit. So how do you go about checking that? Just in terms of these, does that have anything to do with the reparameterization invariance? Do you use that to check that you've done the right thing? Or?
To check that you've included all your terms, you mean?
Yeah, to know how you systematically ordered that expansion.
That's, so I mean right, so I guess what I didn't tell you is these fields have a power counting. So you can just stare at each of these terms and you can see, for instance, that all the terms here scale as lambda to the fourth, and that's leading order. And of course they all also have to be RPI invariants, but you order it by the scaling of the fields. And if suddenly I wanted to couple, like, for instance, a soft field to this term, then that has a higher order scaling, and so it's going to enter into higher order.
So what you can show is that the terms that you keep in one of these sket expansions are RPI invariant up to corrections that are still higher
That's
order
right.
in lambda that you want to keep. Is that the idea?
Yeah, exactly.
Okay.
Exactly. Yeah.
Okay.
Yeah, so, right, exactly. Any other questions before I move on? Okay. So, right. So, if I write down the leading order of Lagrangian for a left-handed wild fermion and a scalar. So this thing is just the box operator written in terms of light cone coordinates. And the line below is just expanded out in terms of components. So just multiply this object out. You can ask, first question to ask is this even supersymmetric? And what are the supersymmetry transformations? Turns out these are the supersymmetry transformations. For now, you can just do the calculation really quickly and see that this is in fact invariant under these. But I will demonstrate to you why these are the correct transformations. You'll notice that they're only in terms of one component. So these are half the supersymmetry transformations that you would expect in n equals 1. Okay, so what does this mean from the SUSY algebra point of view? So recall this is the SUSY algebra for the full theory. If I just expand out this momentum vector on the light cone, so I write it as an expansion like this, right, where this term scales as lambda squared, this term scales as 1, and this term scales as lambda. If I plug that in to my gradedly algebra, I have the following matrix. And what this tells me, the scaling of the different components of the derivative tell me how the charges scale. So in particular, you see that half the charges scale as the hard scale, and half of them are suppressed. So you would expect that the SUSY theory only has half of the usual symmetries linearly realized. So if I want to ask what this looks like in superspace, I can write down the supercharge in terms of superspace. Right, this is the usual thing you write down. Alpha here just goes over 1 and 2, same as before. And if I expand this out, I have something like this. I know this one scales as lambda, and this one scales as 1. And what this means is that the superspace coordinates themselves must also scale. And in particular, they have to have the following scalings. So what this means is that you would expect these two higher virtuality coordinates to not be present in your EFT. Okay. And you can show that what this means from a superspace perspective is that your Sket theory lives on the slice of the full superspace. And we named this thing collinear superspace. I think that may be a bad name or not, but you can actually show this, and this is what I'll discuss later on. Any questions about that?
And I'm just trying to understand, so the ones that go like 1 over lambda,
Yeah.
you're saying those should become irrelevant,
Yeah, and
even though they're getting large in the coordinates.
right. So it's the same. I haven't written it down, but it's the same as what happens in regular space. So the coordinates. So p dot x in your Fourier transform has to scale homogeneously. So the coordinates scale inversely as the momentum. So the suppressed momentum modes correspond to higher virtuality coordinates, which is what you integrate out.
Okay.
Yeah. It's by analog of what you do in regular space. Of course, we'll actually demonstrate this. Any other questions? Okay, so let's move on to actually constructing some models. And I'll talk about gauge theory first. The reason that I'll start off with gauge theory is, well, for one thing, we already know what the IR structure is. It's the same as QCD. If I started off with some other theory, I'd have to actually calculate the IR structure and make sure that there are IR singularities. We also know that the Lagrangian is RPI invariant, again, because people work with this thing in QCD. And what this boils down to is if you write down basically your Sket QCD Lagrangian, but now think of these as gauge fields and gauginos in some adjoint representation, you can ask, the first thing you can ask is this thing supersymmetric under those subset of supersymmetries that I would expect to be present in the EFT? So it wasn't for us trivial how to do this, because if you write down kind of the first thing that you would think of, so the usual Wess-Zumino gauge transformations, you actually get fields that mix different orders of power counting. So you have to do this in a specific way, and it turns out that it's very convenient to go to a non-covariant gauge called light cone gauge. And light cone gauge is defined by this choice, so n bar dot A, where A is your gauge field equals 0. So for instance, if you write down your kinetic term from an abelian theory and expand everything out here, all the Lorentz vectors in terms of light cone coordinates, you can then set all of these terms to 0. It's also convenient to redefine your transverse coordinates in terms of what we call a light cone scalar. And I'll show you why you can think of this thing as a scalar, other than just the degrees of freedom. And then you'll have one non-propagating mode, which corresponds to the suppressed degree of freedom, which you then integrate out classically. And you get some equation of motion, and when you plug this back into your Lagrangian, you get a kinetic term of a scalar that looks just like this. So this is very convenient because one, it means you have, remember we've integrated out we've integrated out / projected half of the fermion components. So we only have one helicity state. It's a complex field, so it has 2 fermionic degrees of freedom. In this gauge, we now see that the physical degrees of freedom are 2 bosonic degrees of freedom. So this is equivalent to an on-shell multiplet. So this already hints that this is the right thing to do, and this gauge might make SUSY manifest, whereas if you try some other gauge, it'll be a lot harder to show this. And again, I'll show this explicitly, but in this gauge, and this is known in the literature, in this gauge, you can organize the vector superfield in terms of a chiral superfield. So any questions about that? All right, so what is the actual procedure? So if you start with, in your full theory, you start with Yang-Mills and you add an adjoint fermion. Here I've suppressed gauge indices. All right, so you have your usual Lagrangian. As I said earlier in the talk, you integrate out the anticollinear fermion, and you're left with this thing that I've now shown many times. The next step is to go to light cone gauge. So to integrate out the unphysical gluon degrees of freedom in the case of a non-abelian gauge theory. This horrible thing here is the equation of motion that you get. You impose light cone gauge, you write everything conveniently in terms of these scalars, and what you have is sket on the light cone plus this added field. And if you go through this procedure, what you can show is that the following Lagrangian is in fact supersymmetric. It is invariant under these 2 transformations, which by the way are the transformations of an on-shell chiral multiplet. And you can just show that explicitly. In fact, if you go through this procedure, this is the terrible thing that you get. This is the gaugino Lagrangian. It's a horrible mess. Maybe it's not horrible, but you would like to write this in a nicer form. But you can show that it's invariant under the SUSY transformations. But we do want to write this in a nicer form, and maybe a form that makes supersymmetry manifest. So to do that, you go to superspace. And what I'll show you next is how exactly to do that in superspace. And effectively what this will mean is you can think of integrating out anticollinear modes as corresponding to integrating out those high virtuality superspace coordinates that I mentioned before. So this is kind of a general thing that you can do for any theory. So you can think of this as some kind of algorithmic approach for finding collinear superspace Lagrangians. So I'll walk you through these steps instead of just reading them out. So let's just think of a chiral multiplet in the full theory. So you have a left-handed fermion and a complex scalar. And remember, this is on shell, so I'm not going to worry about the auxiliary fields because they will correspond to terms that don't exist in the EFT, as will become clear. And this is a really good starting point, 1, because it's simple, and 2, because, as I mentioned before, in light cone gauge, you can apply this to both matter and gauge theories. So just to review, you can think of the chiral superfield as defined by this chirality condition. Here D is the superspace derivative. And then you can write down a kinetic term for the action that looks like this, and in components is just what you would expect. So the first thing to do in your EFT is you want to find, you want to basically do the analog of what you did in components. So the first thing you do in components is to project out the anticollinear mode. So in superspace, you want to find projection operators that project out an anticollinear superfield. And turns out you can use, for this purpose, the same projection operators as you did for components. By supersymmetry, since we do expect a supersymmetric theory, they're just going to act on both the fermionic and bosonic degrees of freedom in the superfield, and just project out what you can think of as a collinear and an anticollinear superfield. If you expand the superspace derivatives in the Sched expansion, again, you'll find that one derivative is not suppressed, and in your EFT, and another one is suppressed. And so you would expect the chirality condition in the EFT to just depend on one of those symmetries. And if you then solve it, just like you would in the full theory, you get the following chiral field, right? So it's got a scalar, it's got one component, one helicity component of the field, of the fermion field, which corresponds to one superspace degree of freedom, and then it's got another term coming from shifting between x and y coordinates. And you can't write down an auxiliary field because the auxiliary field will depend on theta 1, theta 2 terms. Any questions about that? Similarly, in light cone gauge theory, you write down exactly the same object, except that you're now dealing with light cone scalars that are the scalars composed of the remaining degrees of freedom of the gauge field. And these things are conjugated just because of the way things organize. But you can just think of this field as either corresponding to a chiral multiplet in the Wess-Amino model or a light cone gauge field. So the next step, again, an analog to what we did in components, is to integrate out the anticollinear, now full superfield. So you can do that. You can open up Wesson-Bagger and remember that integration and differentiation work in superspace, and you get the following constraint equation. And you can check by projecting out different things that this encodes, for instance, the equation of motion in components for the anticollinear field. So this object by itself is not very useful. You kind of don't know, you can't plug that back into the Lagrangian as it is. And so what you want to do is you want to solve this equation. And to solve it, you kind of have to just guess the form. There's, as far as I know, really no other way to do it. This form you can guess by seeing how how the constraint equation works and how it obeys the various different chirality conditions, etc. So in this case, this is just the solution that you get. Again, it has this 1 over n bar dot partial term, which you can think of as taking the Fourier transform and defining this thing in terms of its momentum eigenvalues. Analogously, it is totally well defined to write down a superspace Fourier transform, and that's what allows me to write a well-defined 1 over d operator. So this is a funny object that I've never seen people write 1 over d operators, but as far as I can tell, it's totally well defined and useful for how we're going to use it. So then finally, we plug this back into our Lagrangian, we do a bunch of superspace manipulations, and we get the following term for the kinetic Lagrangian, which in components reproduces to exactly what you expect for the non-interacting theory. And again, this superfield can be coming from a chiral theory, or with appropriate projections, it can be a vector field in light cone gauge. And as you can see, this only depends on the 2 remaining superspace coordinates that we haven't integrated out. And this same procedure can be extended to other theories. It gets messier, but for instance, if I wanted to do a non-abelian gauge theory, right, I have the usual starting point, And I go through that whole procedure, kind of constraint equation, and you get a Lagrangian like this, where now I've just included gauge indices. And you can check that this reproduces basically this component Lagrangian, except that now we've written something that's simpler and manifestly supersymmetric in those supersymmetries that are linearly realized in your theory. Right, so in particular, it's invariant under these transformations as we expected it to be. Any questions about that?
But at this point, is it still reparameterization invariant?
Yes, yes, yeah. We don't have a good way of thinking about RPI in superspace. The reasons for that is going to like cone gauge obscures RPI. It's a non-covariant gauge. We don't know, full disclosure, we don't quite know how to think of RPI in light cone gauge. In order to think of RPI, you have to go back to Wess-Savino gauge, and there you can see that everything's consistent. But then supersymmetry is slightly obscured. So, but yes, because of that, because we know the component Lagrangian is invariant under RPI, I mean this thing is consistent, and it's not sick. Any other questions? Okay. So let's move on to the Wess-Savino model. And remember, one of our ultimate goals is to study theories of extended symmetry, where we'll have many scalars, and we'll be coupling scalars and gauge fields. So this is another natural question to ask, is if you just have a chiral fermion, chiral multiplet, what is the EFT? So for now, think of the simplest thing you can have. So just have one flavor and a massless chiral multiplet. So the full theory Lagrangian is written in the usual way. It's got Yukawa interactions between the scalars and fermions. And what we found is that this thing does not have a consistent collinear limit. And I will try to justify that for you. It's still very useful to study this thing because it really does highlight the kind of cross-checks that you need to go through, like RPI, for instance, when you construct a new sket. And we have reasons to believe why the obstructions for a single flavor chiral multiplet will be alleviated when we add more flavors, and when we add things like R symmetries when we study n=4. So with that in mind, let's proceed. So in gauge theory, we kind of knew what the IR structure was already from QCD. We did not at least know this for the Wess-Savino model, so the first thing to do is to check, are there actually IR singularities present when you emit scalars off the fermions? Turns out there are. So for instance, if you have a fermion, a scalar that splits into two fermions, you can write down the amplitude for that. You can go through a calculation. It's actually not, you can't just see this by power counting the field, but you can show that there is an IR divergence. However, this object, these things are spin contracted, this thing requires more than one spin state. So we already see that a singularity like this won't exist in a single flavor EFT because we've integrated out one out of two spin states. We only have one left. We just can't write down this thing. And as a result, we don't expect trilinear interactions in the EFT. So we can ask, what about 1, 2, 3 splittings? So it turns out an object like this does have singularities in a single flavor EFT. And when you integrate out the anti-collinear modes, that looks like a 4-point vertex. So if you go through the same procedure in your Lagrangian that we did in components, you find that you have a 4-point interaction that looks like this.
All right.
You good?
Go ahead.
Okay. And what I'll demonstrate to you is that this term has inconsistencies. So the first thing to check is, do the collinear limits from the full theory reproduce the collinear limits of the EFT? So for instance, if we took this object in the full theory, we wrote the amplitude for that, and then we decided to look at the collinear limit. That means we'll take all the momentums in this in this amplitude to have collinear scalings. What structure do we get from that? And then this can be compared to the EFT vertex, right, which is just calculated from the Feynman rules in the EFT. So for instance, here it is. And what you do find if you go through this calculation is that these two things don't match up. You just don't reproduce the right kind of singularities that you would expect. So this is strange. Just seeing it by itself, it's not clear what's going on. But then if you look at RPI, you'll see that this term is also not RPI invariant. So in particular, again, RPI means that the full spinner, so the collinear and anti-collinear modes, after integrating out the anti-collinear modes, this entire object must be RPI invariant, right? So this first part, this is just the free theory contribution. We showed that this was RPI invariant. So in other words, it can be written, that should be can, not cannot. It can be written in terms of some linear transformations that act differently on the U and the U dagger fields. So this is RPI invariant. However, now we've added this interaction term, and if you ask how can I write down some transformation to make this whole thing invariant, you just can't do it. You have nothing to cancel off the variation of this term off of in this particular EFT. This is not a problem for RPI 3, by the way, but for RPI 1 and 2, you just can't do it in the interacting Wess-Amino model.
Should we expect the spinner to be RPI invariant?
So it's not, right? So
So why were you expecting it to be?
So the full theory spinner has to be RPI invariant, and the reason is Lorentz invariance is restored in the full theory, right? So.
But not necessarily for the spinner. It has to be restored for the Lagrangian.
But the full spinner, the spinner should be also RPI invariant.
Yeah, I'm not sure I see why, but maybe it's true.
I think the reason is because it means you have a Lorentz invariant theory, so you can't have the spinner transforming under some non-trivially under some subset of Lorentz generators. So I guess I haven't actually calculated this out, but that's the explanation, and that's certainly what people do in the SCED literature. And then once you demand that the full spinner is RPI invariant, then it's clear that the two different components must transform differently just because the projection operators break Lorentz invariance. But yeah, so so the projection operators pick out different spin states, and it's just not clear that it's just obvious that RPI can't be linearly realized when you have these kind of Yukawa interactions with the projection operators that you've chosen. So this means that maybe we chose the wrong projection operators. Maybe in this case the projection operators have to break chiral symmetry in some kind of way. And this is kind of one of the things that we're thinking of right now, is we're saying, well, the Wess-Amino model has IR similarities. We can show it. Even the single flavor Wess-Amino model has IR similarities. You must be able to write down an EFT for that. Maybe it's not SCED, but you should be able to write down some kind of other EFT. And if you can't, maybe that has implications for calculations that people do where you have like Higgs interacting with fermions. But so yeah, this is one of the things we're currently thinking about. Any other questions about that? Okay. So this is kind of troubling because, like I said before, we want to go to n equals 4. And we now have a possible obstruction for doing that. Right? So what happens if we start thinking about what this looks like in n equals 4? Again, from a supersymmetry perspective, we just expect half the supercharges to be nonlinearly realized. We have an additional SU4R symmetry in n equals 4, so the projection operators will have some kind of non-trivial R dependence. We did some preliminary checks that if you just add more flavors of the fermion, then these problems go away, because like I showed you before, you can now write down, you have 1 to 2 IR divergences, and you can write down trilinear interaction terms, which as far as we can tell are fine with RPI, although we haven't, this is very preliminary, we haven't gone through all the checks.
I haven't really understood that point. Can you say more about why adding flavors helps?
So,
Do
Yeah.
flavors mix up in some appropriate
Right.
way, or what?
so for the very basic reason is this amplitude for an IR divergence from 1 to 2 splitting, this thing in order to exist requires two spin states. In the EFT, we integrated out half a spin state. But if you have more than one flavors, you could imagine this term would couple different flavors of different spin states. So you're just introducing more possible states, and this term will be allowed, which means you can write down trilinear terms. And the trilinear terms, unlike the 4-point interactions, seem to be consistent with RPI and with IR structure.
Even though you can label the flavors, I mean, I would have thought you could just pick out certain flavor labels and, for fixed choices, you would get some problem. So you're relating couplings of different flavors in order to
Right.
get this to work out?
Right. So again, this is, we haven't finished this. This is all very preliminary, but yeah, you're relating couplings of different flavors. You're choosing flavor-dependent projection operators that we don't know what these things look like yet, but we do think that maybe there is some way around it by doing that. But yeah, this is something that's ongoing at the moment.
Okay.
Yeah, so then we would, just from a calculational perspective, you should be able to write down terms like these. So I and J are flavor indices. This is also left and right-handed fields, and leading order of this term should be present, and it seems to be consistent. Okay, so just this thing is really the summary of our prescription. You start with full theory, integrate out modes, you get sket. You can go to light cone gauge, and you have your Suzy-Yang mills on the light cone. And you can do this in components, you can do this in superspace for various different theories. And like I said, the kind of stuff we're thinking about now, we're thinking about what implications of the restrictions are there on the single flavor Wess-Zumino model. Like if you just don't demand supersymmetry, what kind of EFT can you construct? And then, of course, extending to n equals 4. And then, of course, the pipeline dream is things like supergravity, and maybe we can learn something interesting about some of the things the amplitudes guys are thinking of, or maybe this has significant formal implications for soft theorems or things like that. But yeah, that is the status of acid status. Okay, that's it.
More questions?
You talked about some possible kind of pheno implications. What types of things are you thinking about?
So again, very, very preliminary, but if, the idea is if you can understand what goes wrong with the Wess-Zumino model, and you look at maybe calculations people do for like Higgs-Strelong or certain BSM models that have scalar couplings, does that have implications for that? So that's our one, ish direction we're moving in, but at the moment it's not clear. Yeah, at the moment that's also a formal question, but that's, yeah.
I'm just trying to visualize what practical applications this might have. I mean, I suppose if you make a Polino and it then emits a couple of quartz, neutralino or something like that, the quartz could be soft, and then you could maybe use the sket theory in the
Right.
supersymmetric context
Right,
to
right.
organize your calculations. So do you
Yeah.
envision being able to do that sort of thing if you can get this to
Uh,
work out? I mean, it seems to me, though, that
yeah.
in n equal 1 supersymmetry, you're saying there's a problem, and if that, and you need more flavors, so I don't know how you could actually use it in the
Right.
normal n equal 1 SUSY.
Right, so at the moment, we can't, because we need to add more folders, and see how that works. But yeah, that's one of the original things that we thought about. Like, maybe this could be useful for calculations of Suzy particles at the LHC or something like that. Yeah.
Okay, then let's start video again.